Research Computing and Data Services here at the University of Idaho. Yeah, and so thanks for coming. This is part 3 of a 3-part series on machine learning in Python. And I'm hoping everybody can hear me okay remotely. Can I get a thumbs up or a chat notification that you can? Yep. Okay, sweet, awesome. Okay, so we'll go ahead and get started. There's always some technical issues, but okay. So today I'm going to be talking about something called semantic segmentation. So it's a computer vision method for basically classifying every pixel in a scene. Okay, so given an image, you have to give a label to every single pixel in a scene. And you can have, you could be segmenting, one class, which would be like find all the pixels that are Mickey Mouse, for example. That would be one way to do it. Or you could have multiple classes. In the scene that you're seeing here, you have an image, and when you segment it, you are attaching certain color labels to various classes. And so in this case, road, pole, sidewalk, vegetation, etc. In the autonomous vehicle world, this is exactly what they do, right? So if you look at a Tesla doing its autopilot, it's doing semantic segmentation of the scene in real time at like 60 frames a second or something like that, so that it knows every single thing in the scene. And so this is a really important method for a lot of applications. Autonomous driving is one of them, robotics, biomedical imaging. There's a ton of other things. And so I've used semantic segmentation in my own research, and I've got a couple papers where I've used this particular approach that I'm going to show you today on biological segmentation. So just as an overview, so if you attended the previous the previous talks that I've given on machine learning in Python, we started out talking about machine learning basics, and I'm not going to really go over those things very much, but I introduced some toy data sets like the MNIST data set that we used to train a really simple set of machine learning models that could do handwriting recognition. And then we moved on to talking about neural networks and what those are and how they sort of work. And in fact, we trained a neural network to do handwriting recognition in our first talk. And then in the last talk, we talked about convolutional networks. So that's a different sort of neural network architecture that's appropriate for all sorts of things, but especially for image processing, where the weights and the biases that you're training in your models are different. And we'll talk a little. I'll have to go over that a little bit so that as we talk about semantic segmentation. I'm going to reintroduce tensors again, because that's going to be critical to the architecture I'm going to show you today. And in the last talk, we talked about generative adversarial networks, and we developed a program that could generate human faces given a relatively limited training set, and it did okay for what it was. But we're not going to talk about those today. We're going to be talking about this idea of segmentation. And in particular, last time I talked about the PyTorch machine learning framework. So that's a really popular framework right now for machine learning. TensorFlow and Keras, which is now integrated into TensorFlow, is sort of the other major machine learning platform that's out there. And both of them are Python, right? So Python is definitely the language of machine learning right now for a number of reasons, but it definitely has the critical mass, and I don't see that changing anytime soon. So I'm going to talk a little bit about why we would use TensorFlow instead of PyTorch. And I'm going to be talking about the implementation of this neural network, this convolutional architecture, this neural network called UNet, which is the way that we're going to do the semantic segmentation. So we're going to actually implement a UNet, which I show here in the lower right. We're going to actually implement exactly that in code today and run that. And then we're going to train and test our TensorFlow model. So that's what I'm hoping to cover today. Hopefully you're in the right room or Zoom meeting. So this is a slide I shared last time, and it's just kind of asking the question, like, when should you use PyTorch or when should you use TensorFlow? And, you know, all the graphs and diagrams there that I'm showing is really kind of showing the trend that a lot of people are switching away from TensorFlow and using PyTorch these days. 5 years ago, it was totally the opposite, right? But now PyTorch is really gaining a lot of momentum. But there's still TensorFlow is still very actively developed. It's developed primarily out of Google, and it's got some advantages over PyTorch for various things. And in particular, it's really good for deploying things into production. So if you have a machine learning model that you've trained and you want to deploy it as a web service or a microservice in the cloud, or you want to deploy it onto a mobile device, TensorFlow has a lot of libraries and support for being able to do exactly that. There's ways that TensorFlow provides mechanisms for optimizing those neural networks, getting them to run on very, very limited resources, but you can also run them on very large machines as well. So those are the kind of the key advantages. So TensorFlow is an open source machine learning framework. TensorFlow itself is relatively low level, meaning it does really well at optimizing your machine learning on hardware. So CPUs, GPUs, or tensor processing units, which is Google's special silicon that they provide only in the cloud. And so TensorFlow works really, really well with a lot of hardware. You know, you can use TensorFlow to scale to lots of devices and, you know, hundreds of GPUs. And the great thing about it, like I kind of alluded to before, is that you can export programs or your models, which are represented as graphs. You can export that into various form factors that you can put on a mobile device or you know, even embedded in a website or whatever. So and Keras is an open source API that's written in Python that used to support multiple backends. So TensorFlow was one of the backends it supported, but it also supported Theano, and Microsoft has some machine learning framework that nobody uses that it was also a backend, and a few others. Well, as of, I think, Keras 2.4, it only supports TensorFlow in the backend. So they like ditched all the other ones just to focus on support for TensorFlow. And so now, as of TensorFlow 2, Keras is comes with it, right? So when you install TensorFlow, you get Keras. And Keras gives you sort of a user-friendly API to use TensorFlow. You can do stuff all day long in TensorFlow strictly without Keras, but you're going to be dealing with a lot of lower level sort of functions and methods and classes. Keras sort of abstracts that away, makes it a little bit more easy to use. And in fact, one of the advantages of TensorFlow over PyTorch is that with Keras, most people would say that TensorFlow is a little bit easier to learn. It's a little bit easier to use because of that Keras part. Yeah, and it's got a bunch of classes and functions that make things extra convenient, dealing with images, dealing with layers and optimizers, those kinds of things. It just makes it really easy. And some of it you'll see is familiar from the last time when we talked about PyTorch. Okay, so neural network basics, just to kind of go over this again, because it's actually really important. So a neural network, a traditional sort of multi-level perceptron, which is the original sort of neural network that was invented 50 years ago, looks kind of like that, right? Where you have an input layer on the one side, that's the input to your neural network, and you have an output layer, and in the middle you have some number of hidden layers. Hidden just meaning they don't just talk directly to the outside world. They're in between the input and output layers. And you have nodes and you have edges, right? The nodes are neurons, or some equivalent of a neuron, or sometimes they're called perceptrons. And then you've got edges, which are like the connective tissue between neurons. And when you train these neural networks, what you're doing is you're really just trying to figure out how to weight the connections between neurons, and weight the neuron's own what they call bias, so that you optimize those weights and biases within that neural network to give you the result that you want, right? And so by training all of the parameters within that neural network, and this neural network that I'm showing here is absolutely trivial. A real neural network has got millions of trainable parameters, right? And the idea is you optimize that in an iterative fashion over time to, as you train your neural network, as you teach it on data, you're optimizing it. And so that's basically what you're doing. And so what it looks like, kind of breaking it down, is you've got, a couple of input nodes here that are weighted. Each has their own individual trainable weight. You add a bias to that, and then you pass it through an activation function. Now, the activation function, there's a bunch of activation functions out there, and they're appropriate for different purposes. But what we're going to use here today is not even shown here. It's called a softmax activation function. But that activation function basically says, okay, well, given my inputs, what am I going to output, right? And that activation function can behave in different ways depending on the nature of your data and how you want to train it. You might want something that looks kind of like a sigmoid or something like a ReLU. There's a whole bunch of literature about which activation function is the most appropriate for whatever you're trying to do. If you're using the scikit-learn libraries with Python, that's all the code you need to train or to at least instantiate a neural network with 2 hidden layers, one with 50 nodes and the other with 25 nodes. You're specifying the activation function, how your solver, which is your optimizer for how you optimize the weights and biases. That's a thing you can change. How many iterations you're going to train for, and what those layers are. That's really all you need to do to define a neural network. And then after you train it, which is done in that last line, that in fit, you end up with a trained model, if all goes well. Okay, so just to cover this again, to define a tensor is really important, because we're going to be dealing with convolutional neural networks, and they operate on tensors as the data type. Okay, and a tensor is really just an n-dimensional array of data. And they can be multiple dimensions. A rank 0 tensor is just a single value or a scalar. Rank 1 is a vector, rank 2 is a matrix, and you can get to rank 3 tensor is a 3-dimensional shape, and you can go higher than that. But we're going to deal primarily with rank 2 and rank 3 tensors today. And what's important to realize is that an image is really just a tensor, isn't it? It's just a matrix, right? It's just a multi-dimensional array. Grayscale image is a 2-dimensional array that has a width and a height, and then each cell within that matrix has an intensity value. And what you can do with a multi-level perceptron is do this, where you take your 2-dimensional image, you serialize it into a linear set of inputs, and that becomes your, this is a 28 by 28 MNIST image here. Well, 28 times 28 is 784 pixels. They just become the inputs, sort of linearized along the input line there. So that's the way things used to work until convolutional neural networks were invented. And the idea behind this is that the internal hidden layers of your neural network progressively start operating on more and more elaborate and higher level features, right? So you start out with pixels, right, which are just intensity values. Well, in your next layer, maybe what you're doing is trying to identify edges, and then your next layer, eyes, ears, nose, and facial structure at subsequent levels. And the deeper you go, the further along you go, in theory at least, the more abstract and higher level features you're extracting. And then depending on what you're trying to do, whether you're trying to do a classification of that image or something else, I think everything follows from extracting those images at those different layers. Okay, so just briefly, a convolution is really just where you take a kernel, and what you see here, this is a Sobel filter, which is a kind of an edge detector. It's a convolutional edge detector. And the Sobel filters apply exactly these matrices, these 3x3 matrices with these integer values. They apply them as in a sliding window across an image and compute what's essentially like their dot product. And when they do that, they end up highlighting edges. The left matrix here, the left kernel here, as you run that across your image, left to right, and then down, and then left to right, that will identify edges as you go horizontally. The other matrix, as you can see, is just kind of flipped 90 degrees. As you operate that, slide that over your input image, it will detect images in the vertical direction. So it's really just looking for, it's magnifying differences in intensity. So it's basically saying, okay, well, there's a big transition between light and dark right here. Let's amplify that. And that's how you get edge detection. It's actually super easy algorithm, and it works remarkably well, but it's convolutional. So this is a convolutional method. And so what you can do is build up these layers of convolutions, or build up this whole network of multiple layers. And as you go, what you tend to do when you're dealing with convolutional neural networks, and we're going to do that with our UNet today, is you start out with the original size of your image, so 28 by 28 in this case. You run the convolutional kernel across that, and you end up with, you have to specify the number of filters you want to apply. And so that's the number of different kernels that you want to apply at that level or at that layer. And you end up with essentially a stack of derived features. And now what's interesting is the weights and biases are actually the filters themselves. So they're the like, for example, the 3x3 or the 5x5 kernels, those values within those kernels are what define the filters and are the actual trainable parameters of your convolutional neural network. And then sometimes at the end, what you can do is serialize your high-level features at the very end and pass that through a conventional sort of fully connected neural network or multi-level perceptron to get whatever output you want. Here they're doing handwriting recognition using this convolutional layers followed by what we call a fully connected network. Now, one thing I should add is, and this is really important, and we'll see this when we do our UNet, is what you typically do is you shrink at each layer, you shrink the X and Y dimensions of your image to sort of reduce the, because what you're trying to do, right, is collapse it into higher level features. And so you reduce the X and Y width and height of your image while extracting an ever deeper, what they call feature map, which is the number of extracted layers. And to the point where you reduce it to from the here 28 by 28 to 4 by 4. And when it gets to 4 by 4, you know, there's not much of your original picture left, but you have this very deep feature map that should have these higher order features involved. And that's going to be absolutely critical to our UNet. Okay, so enough of a review. So semantic segmentation does this, right? It takes an image, and when you segment that image, you're literally giving it numerical basically identifiers for every pixel, right? So you have a number of classes. Here we've got 5 classes: person, purse, plant or grass, sidewalk, and then building and structures. And so if you look at how that ends up, you know, looking, you know, it's going to be something like this, where every pixel has a numeric value, like 1 or 0 or 3 or 4 or something like that. No longer do you have the red, green, and blue, and no longer do you have that full breadth of intensity. Everything's just, okay, this pixel's a person, this pixel's a sidewalk, etc. So that's what we're going to get at today. And when you do that, you end up taking an image and extracting something like this, where you know not only what's in the image, but you know exactly where it is in the image, right? You can find its boundaries and kind of where it is in the context of the overall image. And again, this is used a lot in autonomous vehicles for exactly that reason, to really decompose a scene to its lowest possible level. And how are we going to do that? Well, we're going to use architecture called a convolutional encoder decoder or autoencoder. And so what this does is it starts out with your pixels at the original size, right? Say we have a 512 by 512 image, pixel image. We start with that. We run a number of convolutional layers, and then at some point we downsample, right? So we basically shrink or have the width and the height of the image and extract a deeper feature map. And we go all the way down until we get to the middle. That middle area is called the bottleneck, okay? That's the point at which you have reduced it to sort of its lowest spatial dimensions, but you have the deepest feature map. But then what we do, so if we were doing like a classifier, we would go all the way down until maybe we're just going to output a 0 or a 1, right? In this case, now we're going to go back up. We've decoded the image. We've encoded the image into a set of feature maps, right? And now we're going to decode the image back into an image, right? And so we go down and then back up. That's called an autoencoder. Super powerful system. They're used for denoising images. They're used for semantic segmentation, all sorts of stuff. They're used in generative AI. So this UNet, by the way, this UNet architecture I'm going to show is used in tools like Stable Diffusion. It's the core convolutional architecture of those generative networks. And so we're going to go through this in a lot more detail, but that's kind of what we're going to do today. Okay, so this UNet, this was invented a long time ago now, but 2015. There was a paper that came out that talked about this UNet architecture. And so this was originally applied to biomedical imaging. So being able to identify tumors, for example, in cells, or identify, particular organs or particular kinds of cells. That was the original intent of the paper. And they had invented this autoencoder or encoder decoder that had this sort of unique shape, this U shape. And so you can see that you do the down sampling all the way down to the bottleneck. That's at the bottom, and then you go all the way back up. But you have these things called skip connections, and I'll talk about those here in a second. Here's a more detailed view of it. So here you start out with, in this particular example I found online, your initial image here is a grayscale image because there's only one channel in it. So this is a black and white image that's 480 by 480. You run it through a couple of convolutional layers, and then so you're applying filters, right? So you're applying filters. In fact, you're applying 64 filters at each one of these steps. And then at some point, you do what's called max pooling, which is like a downsampling thing, where you reduce the resolution of your image from 480 by 480 to 240 by 240. Okay, you have the spatial resolution. Then what you do is you apply more convolutional layers that now with more filters. So now you're extracting a deeper feature map, in this case, 128 features. And then at some point you downsample again and you extract features and downsample again until you get down to the bottleneck. And in this case, we took our 480 by 480 image, we reduced it through that max pooling all the way down to a bottleneck that's only an image that's 30 pixels by 30 pixels, but that has this deep feature map of 1024, which has hopefully these higher order features that are of significance encoded in them. Okay, and then you go back up, right? But the cool thing here is that not only do you go back up, but we do this special step, and this is the magic behind UNet, is that every time you do this this up convolution or transpose convolution to go back up in spatial resolution, you take the tensor from the same level before you went down, and you basically bring it over as it was, and you simply concatenate it to the feature map at that layer, right? So what you're doing, you can see without those skip steps, you would kind of lose the individual highly detailed spatial correlation between any two pixels, right? Because you're shrinking everything down to nothing and then trying to reproduce that again. Those skip connections, what they do is they preserve that spatial information and they bring it over to that layer. So then you're basically creating a shortcut in your neural network architecture, which tells it, just based on the architecture, you can use the deep feature map all you want, right? Take advantage of those high level features if you can. And you also now have access to the spatial information that existed at that same level before you crossed the bottleneck. So you're combining the best of both worlds. You're combining that high resolution spatial information that might be super important, plus that deep feature map. And that's where you get that magic, right? And it turns out that this method has been adopted for a number of convolutional architectures, not just UNets like this, but ResNet, for example, uses these skip connections. And it turns out to be kind of a critical way to get machine learning to go to the next level, is to give it access to prior information before you did some transformations. Just give it an alternate path through the network. So that's the UNet architecture. And it's actually not, it kind of looks complicated, I guess, but it's actually not once you get into it. You can actually not just do two-dimensional segmentation, but you can do three-dimensional segmentation. So in this particular case, this is just output where they were able to use three-dimensional convolutions instead of two-dimensional convolutions to do volumetric segmentation. So in other words, you can actually identify all the three-dimensional pixels or voxels within a three-dimensional space that might correspond to a certain label. And you could go to higher dimensions if that even makes sense. But and it's really easy to go to 3 dimensions. All you have to do is you have an extra dimension on each one of your tensors, and you use a 3D convolution instead of a 2D convolution. And it takes up a lot more memory, so you have to keep that in mind. But it's a totally workable solution, and they use it all the time in looking at MRIs, for example, and CAT scans. They use 3-dimensional semantic segmentation all the time in those methods. Okay, so what we're going to apply our stuff to is actually looking at aerial imagery from drones. I think there's a number of people here that work with drone data and find that kind of interesting. So I thought it'd be neat to kind of dive into that a little bit. So I found a data set on Kaggle, and I'll show you the link to it here in a minute. If you don't know Kaggle is it's a machine learning data science website that hosts competitions, often for money. There's prize money involved to develop, winning machine learning models. But they also distribute data models and other things. So there's lots of machine learning data sets that you could just pull from Kaggle. In fact, I think the face data set that I used last time was stored on Kaggle. So I found this semantic drone data set. And what it has in it is it's got a bunch of just RGB pictures from drones, right, of the ground, and then and it comes with it labels. And so here is an RGB representation of the labeled classes. And here we're actually going to work with 24 classes. Here's just 20 of them, but these are the kinds of classes that we're going to try to segment, right? So trees, grass, other vegetation, people, bicycles, doors, things like that. So we're going to actually do this really challenging thing of looking at 24 separate classes. So this data set, you can see down below is the URL to get to it. There are other ones out there too that are kind of interesting and bigger. This one actually only has 400 images in it. So it was easy to work with. It was only 4 gigs, I think, to download the whole thing. They were 24 megapixel pictures, so they're like 6,000 by 4,000. So I had to reduce their sizes. But this is kind of what it looked like. You end up with this zip file that has, first of all, this CSV The CSV is just a set of labels, right? So it says, the 0th index is unlabeled, and we're going to give it a red value of 0, a green value of 0, and a blue value of 0. So if it's unlabeled, it's going to show up as black. If it's a paved area, it's going to have this other RGB value of 128, 64, 128, etc. And just its position in the CSV corresponds to the numeric pixel index that we're going to work with, right? So 0 through 23. So it's a super slick data set. What you see here is, let's see, here's the original RGB image taken by the drone. Here is the ground truth, right? And I've kind of changed the thresholding of this image so you can see it, but the values of the pixels in this grayscale image, the single layer grayscale image, are just 0, 1, 2, 3, all the way through 24, right? And then if you then take that spreadsheet as a map of how to take those numbers and define them as more colorful, human readable, color coded classes, that's what you get over here on the lower left. And so it comes with all of these things kind of conveniently put in there. Okay, so all the code that I'm about to show you, I have put up on GitHub. If you want to go to github.com/Sheneman, which is my last name, /segmentation, you can follow along there, or I'm just gonna go through some stuff now. So let me stop my share real quick, and I'm gonna go to GitHub real quick. And let me share my screen again. Let's see, where is it? There it is. Okay, so let me bring this up here so that you all in the room can see it.
Disappearing on Zoom.
It's disappearing on Zoom. Of course it is. Is that better, or?
Oh, there it goes.
That's better?
Yep.
Okay, it's just, it can't span screens, I guess.
Does this include all of the data, or do we need to download that separately?
It does not include the data because the data is licensed in such a way I couldn't redistribute it. But you can download it, and if you want to, do you see it okay now? Okay. And if you want, I can, since I had to resize all the images and I changed the structure a little bit for the code to work with it. If you want, I can just, you can send me an email later and or talk to me afterwards, and I can hook you up with the data that I use. I just didn't want to publish it online. Okay, so I put all this in on GitHub, and it's pretty simple. We've got really just four files that we're going to look at. And by the way, there's instructions here on kind of how to install it, how to organize your data directories. And maybe I'll just go over that real quick before we get into the code. So this assumes that you've cloned the repository, and that inside the repository, you create this data folder. And inside the data folder needs to exist the class dict seg.csv. So that's that mapping file to the RGB values that I showed you before. It doesn't need this, but this is the RGB color image masks. That's the ground truth in the colorized form. So if you want to look at how well your model is doing, you can compare it to those. Those are like the colorized ground truth data. And then I break it up into training, test, and validation data sets. Test data and test labels. So the test data folder is just the raw RGB image taken from the drone. The test labels are the grayscale images that contain the labels for each pixel, right? And so they're just the ground truth in that format. It's pretty simple to set up. I used pip to, create a virtual environment for Python 3, installed just 3 things is all you need, is TensorFlow, OpenCV Python image. So OpenC library, it just has a bunch of functions for reading and writing images and make sure that you've activated your virtual environment and run this UNet Python script. And then when you're ready to actually do it, meaning you want to take your trained model and now run it on new data, you just run this inference script. And then that'll produce a set of files directory called raw output. And then you can use this convert script to now map the RGB values in that CSV to a human readable thing. And then I've got information availability where they have a whole sort of research web page devoted to that. They have newer, better versions of this data set too. Let's go ahead and start looking at a couple things. The first thing is UNet. So this is sort of the main your model. And so I'm just going to go through this. There's some basic stuff that you need to import. So importing TensorFlow is usually as easy as just saying import TensorFlow. I usually reduce it to the name TF. And then, yeah, let me get bigger here. I import this library called Twitch. If you're not familiar with Pickle is a Python now that lets you take a data structure and just save it to disk, right? So that's how we can save our history from, and we can save models and stuff using Pickle. There's a couple things like random and seed and sleep that I needed. Import NumPy, and then these Keras models. Now, notice I didn't have to install Keras in my virtual environment. I just had to install TensorFlow, and now I have access to these architecture in a separate file. And then reading and writing training data or different. Okay, so I output the TensorFlow version. It's TF, so I can just print out the version here, and it'll tell you what version we're running. And then I set this. I get different results, right? Because this is a stochastic process. I can set so you get different behaviors. Now, if you wanted to have consistent behavior every time, you would set that to some fixed number, right? And that's useful if you're debugging things. Okay, so here I'm this for 100 epochs, the complete training set, right? So I'm going to pass through the neural network 100 times is what I'm saying. And I'm going to do that in batch. I'm going to send and have it work on, that's its unit of is 4 of those. It turned out on the GPU I was using here that if you have a big GPU with lots of RAM, you can set that higher. You can set it lower. Yeah, you can go down to the training set size. This data came as 400 images. I split out 300 of them as training, and then 50 of them for validation. Okay, but we're going to train on 300, and so that's useful for figuring out how many steps we're going to do by epoch, and that's just a matter of your training set size divided by your batch size. That's how many steps you're going to iterate through. That's just this thing called train generator, and this is a function that I wrote and I'll show it to you in a minute. But what this is a thing that training data, okay? And so TensorFlow has a number of ways. What this generator is, it actually emits, it's just like pipeline that will throw you more training data. And I'll show you what that looks like here in a second. Paths here. So I give it the batch. So I give it, where the data is. It's in this data folder. My data and the labels that are associated with them are trained data. And remember, this is a supervised machine learning method. So you have to provide the raw data and ground truth so that it can learn an example, right? And then the number of classes for mode, the images I'm providing it are in color. So they're the target size 12 by 512. By 4,000 to the same aspect ratio, but I didn't stretch it at all. I basically just took 512 by 512 picture that was left. Now, if you are going to use semantic segmentation on very large image, memory in your GPU to do that. So what you typically of individual patches that are of the right. So one image as you pass through might be patches that you split up. And there are libraries in TensorFlow or Keras patches, but for simplicity, I just went through and resized everything beforehand, right? From that original big thing. Okay, then I define my model. I just say model equal unet. Now this unet comes from a different file, and I'll show you what that looks like. I set up a model checkpoint so that I can, at the end of every epoch, I want to save the current model as it stands as a file, and I only save the very best one, right? So if at any particular epoch you haven't improved, I don't save that in that callback. And then here we go ahead and call this model fit generator, which actually does the actual training of the neural network right there. And then when we're done, we save the model, and we can save the history as this pickle file. That's useful if you want to know kind of what the learning rate was, what accuracy was over time. It gives you that sort of time series data. Okay, so that's it, right? That there's a little bit more behind the scenes, but really all you're doing is setting some parameters, your hyperparameters for how you're going to train. You set up this generator to make sure that you're passing your training data through, and then you instantiate your unet model, and then you train it, and then you save the result. And so it looks like maybe harder than it is, but when you get into it, it's not too bad. Okay, so let's go back here. So one of the things that we saw is, oh wait, did I pick it back here? No. Yeah. Okay, so I'm going to go to this unet. I'm sorry, not unet model. Okay, so this is where we actually define our architecture for the unet. Now you remember it's that autoencoder that goes from sort of large to the large spatial resolution down to a bottleneck where you have small spatial resolution but a deep feature map, and then all the way back up and you have skip connections. Okay, so remember that image, because that's exactly what we're going to do here. There's the paper that it was cited it, and then I grabbed some code that somebody had as kind of the initial implementation in TensorFlow, and so I just cited them there. So basically what I do is I just say, okay, I'm going to define this function. This is just a function definition in Python, right? I'm going to define this function called unet. I'm not going to do anything with pre-trained weights here. And we're going to set the input size. So the input tensor that this model expects is an image that's 512 by 512 by 3 deep, red, green, blue, right? It's a color image that we're passing. And then we do the encoder. And so what this is just a series of convolutional blocks, right? And I put some comments here on exactly what size of tensor that convolutional block expects as input and what size it expects it will output, right? And so what we do is exactly what I described before. You have a couple convolutional layers. You're applying 64 filters with a kernel size of 3 by 3. If you just have a single digit there, it implies that it's a 3 by 3 kernel. I specify the activation function I'm going to use. And I say padding equals same. And this is similar to what we saw in the PyTorch example with the GAN that I showed last time, is that as you slide your kernel over the image, if you don't pad your image first, the resulting image is going to be a little bit smaller every time because that padding has to start actually on the image. It can't start off the image. So it starts on the image. And so what we do is we say padding equals same so that the resulting tensor from this convolution is the same size. Okay. So all it is doing is padding the image prior to the convolution. This just initializes this particular layer to a normal distribution. I'm not sure that really matters. And you basically specify here that what the input to this layer is. Okay, the input to this layer is this inputs thing that we specified here. Okay, and so what you're basically doing is just passing along the output of the prior layer as input to the next layer. And then you come down to the max pooling. And so what this does, max pooling, it just takes a 2 by 2 rectangle of every image. It finds out, so 2 by 2 is 4 pixels, right? 2 pixels by 2 pixels. It finds out the maximum value, intensity value in there, and it uses that as the value of the next tensor that it produces. So by doing that, you're basically shrinking a 2 by 2 4 pixel grouping down to 1 pixel. And so by doing that, you're shrinking it both in the X and the Y direction. And that's how you get your size starts to shrink as you go down your UNet, right? And so it's this max pooling. Go ahead.
Sorry, I didn't mean to interrupt you. Which libraries are we pulling these functions from? Are these just Keras functions?
Yeah, these are just, so if we go up to the top, we just we do this Keras layers. I'm importing everything from this Keras layers, and that's where you get like conv2d and things like that. And so we just repeat that, right? So these blocks, these convolutional blocks are all pretty much identical, except that the size of the input-output tensors are different. That's all. Until you get down to right before the bottleneck. The only thing that's different here is that I add a dropout. And a dropout, what that does is introduces brain damage, basically, to the neural network. And it does it on purpose because it helps prevent overfitting of your model. If it learns certain paths early on as it's training the neural network, it might start relying on those particular parameters that it's trained on a little too much and not be open to learning other paths, right? And so we actually we drop out some of the connections that we learned in previous iterations. And this has been shown to improve your model's ability to generalize to data it's never seen. It prevents it from overfitting, is to introduce that kind of, I call it brain damage. And then finally, so we get down to at the end of this convolution, we have an output that's 32 pixels by 32 pixels by 512 feature layers, right? And then we reduce that one more time, and at the bottleneck, we end up with we end up with a 32 by 32 by 1024, and that's our bottleneck. That's as low as we're going to go in this case. We could go lower, but that's as low as we're going to go. We add another dropout on the other side of the bottleneck. So basically, we have a dropout on the left side and a dropout on the right side. And you can put more dropouts or less. And then the decoder basically goes back up from your encoded feature deep bottleneck, and it creates the decoder. And that skip connection is handled here by a simple concatenation. So what you're doing is you're just concatenating one tensor onto the other tensor. And you're doing it in a particular, you have to specify which axis you're doing it in. And the axis that we're concatenating them is along the feature map, right? So we're concatenating the feature maps. You can't concatenate things of different dimensions. You have to make sure that the same dimension. And so, but with the feature maps, they can be an arbitrary number of those. And so we're concatenating the feature maps. And so that's how we get the skip connections. We just go up, and again, it's exactly the same. There's no real difference until you get to the output layer. Now, the output layer, you're back up at this point to a tensor that is 512 by 512, which was the original size of your input image, with a feature depth of 64. And then, but what we want to do is we have 24 classes, right? We have 24 different classes like bike, person, grass, right? Those are our 24 classes. We're actually going to in our last convolutional layer, create a layer for each one of those classes. And so that's where that 24 comes from. And we're going to use the softmax activation function. You can see up here we used ReLU. Softmax is probably more appropriate for an equal spread of not preferring any particular class over another, right? But so it's an appropriate activation function for a multi-class problem like this. And then, okay, so we've got all of our layers, or we have our inputs, which are our what went into this. So we have our outputs, which is this conv10 output layer. And then we call this model function, which just returns a model object. And then you have to compile your model object. You specify which optimizer you want to use. In this case, I'm using the Atom optimizer with a learning rate of 0.0001. And so what that optimizer, there's a bunch of different optimizers you can use, but this is the algorithm that goes back and tweaks all the parameters in your filters, right? There are advantages to some and disadvantages to others, and Atom is a really popular one. I just used Atom in this case. But really importantly, what we're doing here is what we call, we have categorical results, right? We have these different classes, these different categories. And so our loss function that we're going to use for this is called categorical cross entropy. And so we specify that, and we specify which metrics we're going to pay attention to as we train. Then I spit out a human readable version of the model architecture here. And then if you provided pre-trained weights to this, when you defined it, you can just, now that you've defined your architecture, you can just throw your weights onto it, right? So if you have a prior model that you've saved, you can load those weights and just tack it on here and be off and running. And so sometimes you'll do that, right? You'll train a model to a point and then modify something in your algorithm, or maybe augment your data, and then continue training beyond that, right? With those new configurations or that new data. Okay, so that's defining the entire model. Okay, and so again, it looks like a lot of code, but it's all just kind of copy and paste, and as long as you pay attention to the tensor dimensions. Then real quick, I'm just going to show you, we're kind of getting low on time already, but I'm just going to show you this. These are helper functions, these UNet data functions. So for example, I import this image data generator from Keras. And what that does, again, this is the function that we called from unet.py that creates our trainer, our train generator. And what it does is instantiates an instance of one of these image data generators from Keras. And then it does this thing called flow from directory. So what I want to do is I want to basically tell it, here's the directory with all my training data. Flow this through the generator, flow it from the directory as you're training, right? So it just creates this generator that flows it from a directory. There's other ways to structure this, but this one works really well, especially if you have a lot of data. It's best to just kind of point it to a place on the file system and say, just flow that through when you're doing your training. I specify color mode and a few other things. Now, you have to load two things, right? You have to load your original red, green, blue images, and then you have to load your masks or your labels, right? And because as you're training, you have to compare your prediction against the truth every time, right? And so you have to load those masks. They can be called masks or labels, but you do the same thing. You flow it from a directory. In this case, the directory is in a thing called the mask folder, which is just has a different path. And then what you do, which is kind of cool, is you use Python's zip function to zip those two things together, and then you create this little yield thing that basically it takes your image, divides it by 255 so that we can deal with floating point values. So these are, again, 8-bit red, green, blue images. If we what we want to do is divide that by 255 so that the numbers that you're dealing with are in the range of 0 to 1. It's just everything works better in that way. And then for the mask, we do this thing called one-hot. So one-hot encoding. What that really means is you're basically creating a set of layers. Each layer represents a class. And if something is a particular class, there's a 1 in that layer, right? So it's a kind of this sparse matrix representation called one-hot encoding. And it's useful for these kinds of things. And so that's what I do here, is do that one-hot encoding. So now I have our masks in that one-hot encoding method, and then we have our training data as these tensors. And then I've got some other things that that basically help with loading training and test images. Finally, at the end, so if you're doing your inference, right, you're trying to run your model on new data and get an output, this is the function that ends up getting called. And this argmax is just a NumPy function that takes the three-dimensional array and it collapses it. It basically argmax will give you the index of the layer that had the maximum value. And that's how you collapse that back into a grayscale image with values between 0 and 23. And then we save that as an 8-bit image, a grayscale 8-bit image, because our input for inference is a RGB image, our output is a grayscale image. Okay, so with that, let me stop sharing real quick and then bring this guy up. Okay, let me share that again. So we're just going to look at some, actually execute this thing real quick. Okay.
One of the most interesting bash prompts I've seen in my life.
Oh, good. Okay, so this is on a machine at Research Computing and Data Services. It's got a GPU on it. And here's where I've got all of that code. I've got my virtual environment set up, and I think we're ready to go. Remember, if I go into the data directory, more or less, this is what you see, right? We have our train data and our train labels, which is really all we're going to use here. We've got the class dict seg is there. So everything that we needed that we referred to. And so if I now all I have to do is say Python. On this machine, I have to specify the version. Unit.py, we'll go ahead and get it going. And so you'll see a bunch of spew about stuff. those are mostly just, okay, so let's just back up here. So these are just warnings, right? These are basically, if you ever run TensorFlow, you'll see these kinds of warnings all the time. Basically, it's saying that this TensorFlow binary uses certain, processor commands, and you make sure that you're supporting it. You can usually ignore it. The GPU that we're using here is an NVIDIA RTX A4000. And then what I'm doing here is spewing out the actual convolutional layers of our UNet, right? So this is the model summary output, right? And this will tell you in a human readable format, like kind of what it looks like, how it's all connected, and how many trainable parameters are at each level. So you can see that at the bottleneck, there's almost 1 million, 9 million trainable parameters just right there at the bottleneck, right? And then it reduces again. It'll tell you your total parameters, 31 million trainable parameters, and then you just kind of let it go. And you can see that if you look at the bottom there, it's already on the second epoch. So this is the second pass of the training data through the trainer. I think I have it configured to go to 20, but we don't have time for that. But what I will show you is, we'll just let that continue to go. What I will show you is what the results look like. So let's see. Okay. And then, sorry, gotta find my cursor over here. Okay, so this is kind of what we got out of this particular exercise. In this particular, these are just examples. So this was the input, right? So this was the input drone imagery. You've got some sort of sidewalk, some grass, some people, some bikes, some walls, some fences. This is the ground truth. So somebody went through and like hand labeled these things to get the ground truth. And there are labeling tools out there, and we could talk about that ad nauseum, but there's all sorts of great labeling tools to do this pretty efficiently. And then what you can see is after 100 epochs, this is kind of what our model did. So it definitely was not perfect, but it got some things right? So it got, for example, it was able to detect that this was some sort of sidewalk or walkway. It was able to detect that this is grass. I think it started to figure out that this was a fence, but definitely wasn't perfect. The model that we're using is pretty simple. There's a lot of optimizations that we could do, but the biggest problem, I think, is that we only had 300 images to teach it, right? And what I would recommend is having at least 10 or 20 times that many. Give it way more examples. Now, if you don't have them, what you can do is augment your data. And Keras provides these resources for taking your data and transforming it, both at the same time it transforms the raw data, it transforms the mask accordingly. So it'll rotate it, change various aspects about it so that your original 300 might actually get extended to be more like 30,000 if you augment enough. And so that would be something we could do. I didn't do that here. So I think we had kind of limited training data. So you could see it did okay, but not great. Here's another one where it got most things right. So this was the original input. That's actually a color image. You can't really tell. Things probably taken at low light. And it was able to hit the ground truth, and the final result we're starting to get in line. Definitely got the road correct. Started to find the trees and fences. And then here's the third one. And again, you can tell that it was starting to figure out that this it was probably a building, but it really couldn't tell the difference between that and the sidewalk. I've seen examples of really well-trained UNet models that are used for aerial imagery like this, where it's pretty spot on. It's not, it's never perfect, but can do a lot better than what you're seeing here. But for this really simplistic tutorial, I think it did okay. Okay, so that's all I had. Maybe we stop for questions and then call it. Yep.
So is there a danger when you're using augmented data that the device will start to develop the wrong kind of connections, I guess? Because that's internally I rankle like, oh, we have more data just because we rotated it. That doesn't seem like it's going to work that well.
Yeah, I mean, it'll do a bunch of stuff. So it'll like zoom in, zoom out, rotate. So the idea is that you get yeah, you're able to add more to it. I mean, I think the ideal thing would be to have just more real data, but if you can't get that, augmentation is a reasonable approach, I think. But yeah, I don't know if any studies have been done to sort of look at how that might bias your overall training, but that's an interesting question. Yep.
Is there a limit to how small the object you're trying to detect in drone imagery? Like if you're, that like searching for nests, or I know one of my lab mates is searching for birds in trail cans.
Right.
Small.
That's pretty small, although I've seen it, if it's got a pretty clear shape to it, even if it is small. I mean, if you as a human can see it pretty well, there's no reason that a machine learning model couldn't do at least as well, if not better. But if it's like pixel sized, probably not, right? I mean, it has to have some sort of identifiable characteristics that you as a human could, identify and classify. And if you can do that, then a machine can do it. Yeah, for sure. Yeah.
Is there any disadvantage or advantage to the number of like different types of things we're looking for? Like for this example, you said we're looking for 24 different things. For example, we're just looking for birds. Can we train it to be better? I
think it would be way better if you had a limited set of classes. Yeah, because it's got to juggle training weights for a lot of things that look kind of like each other, and like the more yeah, exactly. So the more classes you have, probably the more elaborate your network's going to have to be, the more training data you're going to have to provide. If you're only dealing with one or two classes, it'll be a lot easier. Yeah, for sure. And you'll get more accurate results, I think. So there is an example of this same data. I think they use the same data set, but they only went in and classified 5 different classes. And I didn't use that for this, but my intuition says that it would be a lot more accurate for that. Yeah, just because there's less to have to decide between, right? Because what it's doing is trying to decide what is this class, and it's going to be wrong some number of times. And if you've got more classes, there's just more chances for it to be wrong.
Right.
Yeah.
If hypothetically speaking, I'm bored over spring break and I want to take a shot at that 5-class thing, how did you go about transforming your images to be like the cropped and stuff?
I used Image Magic.
Okay.
So it's a Linux utility, and you install that. You probably have it for Windows too. I don't know what you have, but okay, yeah. So if you install Image Magic, then there's this tool called Convert, right? And so you just from the command line, you just say convert, give it the input image. You say I did -resize 13%, which reduced it to approximately the right size, and then I cropped it the 512 by 512 upper left-hand corner. Okay. All in one command, I was able to do that with Image Magic.
Okay, and then you can just use wildcards, so it goes through the entire thing like that.
Yep. Just use wildcards or create a little bash loop or something. Yeah. But Image Magic is your friend. Yeah.
So is the main like a limiting factor in a system like this from being better, just computing power and time? Basically, like if we could extend this to 10,000 epochs instead of 100, we know it's going to be better, right?
Yeah, as long as you don't start overfitting. What I didn't do in this case, what you normally do is at the end of every epoch, you run your model as it stands against data it hasn't seen yet, against data it wasn't trained on,
right?
To see how well it does. And
it's actually working.
Yeah, and so what you should see is your training is, your training accuracy is improving and your validation accuracy is improving. So it's getting better on data that it was specifically trained on, and it's getting better at data that it hasn't seen before. But you will get to a point where it will start improving so well on only the data that it sees that your validation accuracy will start dropping off. And so at that point, you know that your model is as fit as it's going to be. And any more training will actually mean that it won't do so well for data it hasn't seen before. It stops being able to generalize its algorithm and starts getting super specific to just the nuances in the specific parts of the data that it's seen in the training set. And so that validation is critical to do that validation so that you know when to stop your training. Yeah. So no, more epochs isn't necessarily better.
Okay.
What you could do is you could have deeper feature maps. You could have more convolutional layers. You could increase the width and the depth of your UNet. There's a bunch of work that's been done with UNets that have modified that basic architecture to make them, there's something called wide new UNet, there's something called deep UNet, there's something called UNet with a ResNet backbone. I mean, there's a bunch of people that have improved it. And there's one called UNet++. So there's all these improvements to the UNet model. So you can improve the basic architecture of your neural network. You could play around with your hyperparameters like learning rate and your optimizer, and those things will make some difference. But the best thing you can do in most cases is just give it more data. The more data you give it, and that equates to more computational time, right? Because it's got to process all this. It's got to go through more things. Yeah.
You get a chat question.
Okay. The aerial image resolution seems pretty high. What's the best strategy to deal with lower resolution? Is the UNet close to real-time segmentation? Yeah, so let me answer the second part first. I think it's not real time, and as far as I've seen, so I'm looking at inferences on this hardware of like, it takes about a second maybe to do an inference, which if you want real time, you probably want about 20 or 30 times that. So you can do like 20 frames or 30 frames per second. So you could actually segment video. There are other algorithms that can do real-time segmentation, like YOLO v5 can now do real-time segmentation, but I don't know how accurate it is as compared to UNet. And then the question is, does this work well on low resolution? I think so. I think it would work okay on low resolution data too, as long as, again, there was enough detail in the low resolution images for a human to pick out the important features and to classify things. If that's the case, then I think it would do pretty well with lower resolution images. And again, if you want to do with higher resolution images, typically what you do is you take a large image and break it into patches and then process every patch separately. Because at some point your tensors will get so big you'll run out of GPU RAM. So okay, well, thanks guys. I appreciate it. It was fun. Yeah.